Hello students, these are some review notes for chapter 3, which we did the radical chain halogenation reactions. I know there was a little confusion about this in our last activity, so I thought I'd review a few things. So let's give a typical scenario. So in this particular sample of radical chain halogenation, we're going to react bromine with propane in the presence of light and heat. And of course what the light and the heat do is that they initiate the reaction. Well, how do they initiate it? Well, we always take some sort of halogen in our reactions, and when we subject them to light and heat, they break down homolytically. So we use our fish hook arrows and we generate bromine free atoms which have an unpaired radical, an unpaired electron, which we often call a radical. All right, and so that initiates the reaction. So that's happening in solution along with propane, and so there's just lots of these bromine radicals once they start forming around. So then what happens in our propagation step, which is step number 2, is that we can show this mechanism by one of these reacting. Now again, remember, since we're generating two of these here, that they're each sort of doing this in parallel, and there are probably lots of others, but we're just going to follow one. So the bromine's going to react, and we're saying it's reacting with propane. All right, so I'm going to draw propane like this to highlight these two central hydrogens because we know that's going to most likely react with a secondary group. And so this is where we get our first propagation step. And in this first propagation step, one of these unpaired electron molecules or atoms that we've generated is going to react with our organic compound, the propane. All right, so again, we're going to form a bond. So we often show this bond formation where we have electrons from the two fishhook arrows coming together, and then one of the electrons is going to stay with the carbon. So that would yield HBr. Remember, that forms because the hydrogen, generating a hydrogen radical is really unstable. Generating a propane radical is more stable. All right, so we're going to generate carbon that has that unpaired electron, that radical that's there, and this guy as well. All right, so those are our two products, hydrogen bromide, and also this propane radical, or propyl radical here on the second. Remember, in a propagation step, we're always consuming one radical and forming another. So in this case, we're consuming the bromine radical to form HBr, but we're generating another one, this propane. All right, and so this propyl radical, and then we can redraw it down here again. All right, so once again, we're going to generate a radical while we consume this radical as well. Now in the second propagation step, what we know is that in this big solution there is more bromine. In fact, there's excess of it, so it's floating around, and so because the radical here is fairly unstable and wants to react, it'll react with another bromine. So we can draw our curved arrow to show a bond that's forming between one of the bromines, so those come together, and then the other bromine is going to keep its electron. All right, and so then that allows us to generate a product, which is a bromo group that's added to this guy, and then all propagation steps regenerate a new radical. All right, so again, once again, we're consuming this radical by reacting with bromine, we're forming a product, and then we're regenerating another bromine. All right, and so then this bromine could come back up here and participate in step 1 of another propagation step, reacting with another propane molecule. All right, and so this cycle of step 1 and then step 2 and then the bromine coming back here would continue for a time until those radicals and free atoms, until they reacted. All right, and so that's really the second phase, this propagation step. And then finally there is a chain termination steps or reactions, and that is really when you get any two radicals coming together, right, to form a product that does not have a radical. And so again, if we happen to have two bromines side by side and they're reactive, they would actually form Br2, all right, which we see here. That would be an example of a chain termination step. Let's assume that one of the radicals that we generated, the propyl radicals that we generated, happen to be nearby a bromine radical. Again, those two could come together, and when they react, we generate a new product that does not have an unpaired electron. Br2. All right, so again, and so there could be other possibilities, but the main thing in termination steps is that you have two radicals that come together, and then they actually terminate the radical halogenation by forming a product without an unpaired electron. All right. So in contrast, up here in the propagation step, every time we react, we are regenerating a radical and unpaired electron. Termination steps, these two and others that are possible, would not generate those. All right. So again, initiation, propagation, termination, those are the three types of reactions. This one's pretty much always the same. You have a halogen breaking apart. In the propagation, you have step one, where one of the halogens generated from up here, it comes here, reacts to generate a new radical. This one reacts in step two with another molecule of the halogen to generate a product, and then also another bromine. So that can repeat, and that happens indefinitely. And then finally we get termination steps. All right, so you want to know these three reactions as types as we move forward. And then one other thing that I'll show you is another sample set of calculations from our in-class activity, class 5. And you might remember this table from it. And again, it gives you, for these three halogens, it gives you their selectivity at the primary, secondary, and tertiary groups. And by the way, in class I mentioned these. We didn't have time to go over it, but it won't be important for the quiz or further. But just know that a benzyl group is basically a six-membered ring, right? So, and then it has a CH2 here with a radical, and so that would be a benzyl radical. And then an allylic group is where you have carbon-carbon double bonds. Remember that is an alkene, right? And then hydrogen here, and then the radical would be there, so that would be allylic. And there's some importance to the fact that we have a double bond, single bond, and then that radical that's forming there. All right, but those are just for information and won't be useful for the quiz. Okay, so let's think about this propane yielding two different types of monobrominated compound. All right, so let's draw out propane. I'm going to use a blue font for secondary hydrogens, and I'll use a red hydrogen for any primary. Right, this one looks good. All right, so hydrogen there. So what we find out is that if we look at this, we have a total of 6 red hydrogens. All right, 6 primary hydrogens, and we end up with 2 secondary hydrogens. All right, so that's important because ultimately what we can get is we can get 1 or 2 propane molecules where we have a bromine that's attached to a secondary group, as we see here. And I haven't drawn in any of the hydrogens purposely, or we can get a bromine that's added to one of the two ends, either this carbon or to that one, to give a primary group. All right, so let's go ahead and calculate then the selectivity of bromine and propane using this information, the same table. Okay, so one of the ways that we can calculate this, and let's do it first for our primary groups, is that we know we have 6 primary groups. We're going to multiply that by, for bromine, this one value, that's our selectivity that someone else has already figured out. That gives us a 6. Remember, that's for the primary. Let's do it also for the secondary. We said we have 2 of those hydrogens. And again, how do we get that hydrogens? Again, there are 2 hydrogens connected to a secondary carbon. And again, for each of these carbons on the end, they're primary, and they each have 3 hydrogens attached to them. Right? But notice that the selectivity for bromine for secondary is 100. This would be 2 times 100, and that would be 200. So then we would say that the product ratio is a way that we can think of it. I'll switch to black now. Is for secondary to primary, it's basically going to be 200 to 6. That is, we'd be 200 to 6 times more likely to form a secondary group than this one. So again, 200 to 6, and that's the product ratio. Again, we get these values from using a table like this, preference, which some scientists have determined for these, and again looking at these for various halogens and for the various positions, and then also considering the number of hydrogens that are primary and the number of hydrogens that are secondary. Alright, so you want to be able to do this for any set of compounds, again, that are primary, secondary, and tertiary. We're going to focus just on those, but being able to determine the number of hydrogens present for each type, and then also using the selectivity values. Alright, so I hope this has helped a little bit, and I will see you soon.